Hi everyone, I am Robert Sassu, core developer of MultiversX, and today we will be speaking about the virtual machine, the smart contracts in general, DeFi blocks, modules, interfaces, tokens. MultiversX is a scalable blockchain which resolves the blockchain trilemma, and on it there sits a virtual machine built which runs WASM smart contracts, and they can be used to run your applications. And in today's discussion, we will speak about how do we achieve amazing speeds, how can you build smart contracts easier, and how can you write your contracts by using existing building blocks. So let's just jump it in. The title for today is "It is easy to build on MultiversX." So we want to reach internet scale execution. And for this, we had to come up with a suite of innovations. The virtual machine currently is the fastest in the blockchain space. It runs smart contracts faster than anybody else out there. We have smart contracts which can be developed in multiple languages. We mostly support right now Rust, as Rust is a superb language to build smart contracts, and we have a Rust framework SDK which abstracts a lot of operations for the user, for the developer, and the developer have to focus only on the business logic. At the blockchain level, we have smart accounts. So any account is not only just a simple user address and balance of a base token, but you have the ESDT token standard where your accounts are keeping actually the tokens. This helps a lot on composability, and this helps a lot on multiple DeFi operations and easier user interfaces. This is where it comes with tokens as well. Furthermore, we have a lot of in-protocol built tools like the Guardian support, in which a user can put a Guardian as his own on top of his own address, and through a 2FA system offered by the Guardian service, your actual every transaction you execute needs to be double signed. So it is more protected than any other chain out there. Furthermore, we have features such as relay transactions directly implemented in the protocol, which can help builders to offer relayer services, this meaning that gasless transactions. Users do not have to pay gas with their own EGLD token, or if they do not have own EGLD token, they cannot pay. So they will use the relayer service, which can be based on a subscription model or other kinds of models. But actually, relayers can wrap the user transactions in a relay transaction in a safe way at the protocol, and they will be executed at the protocol level, such as user transactions fee paid by the relayer. These are all amazing stuff. Today we will mostly talk about virtual machines, smart contracts, and the tokens, and especially why it is easy to build and how to build. So this is like the basic architecture for our virtual machine. The virtual machine sits on top of the node. It communicates with the node through a blockchain hook, and it gets his inputs as a VM input and creates a VM output. All execution on the VM is sandboxed. Everything is executed into a cache, and only when the whole execution is complete and secure, it is written to the blockchain level. This is one of those things which helps us to achieve those kinds of numbers, those kinds of high processing numbers for smart contracts, and other a multitude of other small innovations as we take a pragmatic step on how to build such products like the VM and the Rust framework, and we are taking a pragmatic approach of resolving the multitude of issues developers are facing when they are developing smart contracts. So what we want to do is to help developers build easier and safer code, because that will drive the number of developers on the chain, and they will drive others to use this. So the VM has at least two parts. The actual VM is written in Go. This handles the communication on the node, offers VM API for the developers, for the smart contracts. And then we have the great WASM engine, which is actually the WASM, which runs the WASM binary through the single pass streaming compiler. The best speed we could achieve right now is 4,223 swaps per second. This means token transfer, executing the DeFi liquidity pool AMM smart contract, and transferring back the results to the users. So it runs on the whole smart contract, which is currently sits on the mainnet, and the number was achieved on a MacBook M1. How can we do this? Is that we actually we do not compile the smart contracts at every time, but we actually compile a smart contract, create an instance of it, and we keep that instance as a runnable object, which will be run at multitude of times when it is needed to be run. So you do not have to compile and execute, but you compile your WASM, the system compiles your WASM code only once, and then at every execution, it just spin up that instance, cleans from its memory, and starts running again. These kind of instances, they are actually binary codes, so they are pretty close to how fast a bare machine execution can happen. You can think about how many operations there are in the DeFi, in a DeFi contract. There are multitude of those that kind of operations inside. There are multiple of reads and writes to the storage, and everything involved around it can be executed at such a fast speed per second. So it is a fun time to be and build on MultiversX, and we can ensure that a multitude of DeFi operations, a multitude of fintech startups can run their operation on MultiversX without any issues. So why it is easy to build on MultiversX? As I said a few times, we take a pragmatic approach on how do we help developers. What does it mean actually? Is that we not only are building the virtual machines, we have our own product, and we try to innovate in such a way with our product that to reach new heights, let's say, like this. So we do not want to copy existing algorithms from here and there, but we always tend to improve those. Because of this, as we build the smart contracts, we see what kind of common modules we would need in order to build easier. What could the VM or the Rust framework or the chain actually offer more information or algorithms, for example, in order for the builder to write less code. That's why the number of opcodes we actually have on the VM is much more than EVM or on other chains. We have a lot of libraries which we implement it in Go, or we take a audited standardized library implemented in Go, and we offer endpoints which can be called by the smart contract developers and all the execution is done in the Go binary, which is audited and secure. Such are the safe math and the big numbers, and even further the maps. So if you look in EVM and you want to work with big numbers, then you have to work with the U256 structure, and that's only for 32 bytes, big numbers. And on that structure, if you want to make mathematical operations, you have to use a library, and you have to search for a library smart contract and to execute things on that library smart contract, which is, yes, it might be audited, but it is much slower than using a library built in Go, which you can directly code. So, and the safe math we offer for big numbers like big ints and recently big floats, it's a vast, so you have all the operations required, and all these information and execution happens at the bare bones speed. One of another thing we have improved, it's called managed buffers. So a smart contract can write into his own buffer, which is, let's say, limited only by the guess. But writing and reading from this buffer is super cheap, as this buffer is used as only cache and is not written into the storage. So it's not like I have a variable and I have to change this kind of variable 10 times in the current execution. I do not have to write the change for that variable 10 times into the chain. Moreover, it saves gas, and this helps also smart contract to smart contract calls. By the way, about this, on Ethereum there is a new improvement proposal. They want to implement such managed buffers in EVM as well, but we'll see how many years will it take. The idea is with managed buffers that it helps you for smart contract to smart contract executions. As before you want to call another smart contract, you in general you want to save some information, and at least you would like to save that information into a cache. And then after the execution of the smart contract, you read from this, you read from that cache, you do something with the results from the other smart contract call, and finally write into the storage. Managed buffers, you can do that pretty easily, and this kind of managed buffers, they are tied directly to your smart contract at the execution of the smart contract. They are always clean, and then you can add information into it and delete information from it and choose whatever things you want to write into storage. For everything from big numbers to maps to vectors to managed buffers, you can simply call a write API, and then the VM will resolve the actual writing into the storage, and you do not have to, let's say, take and copy the information from the buffer and send it to the VM in another way, as the VM has access to those kinds of pointers. So the VM offers in a sandbox environment a complete execution environment interface, total memory management for the smart contracts, and big number arithmetics as well. Memory management is again a super important feature which makes developers do not have to care about it. They always have memory. They just have to write their code. They do not have to think about memory allocation or deallocation, as the VM, the instance, will handle for them, and it doesn't cost gas actually. So they do not have to think about it. So it's much easier, and because of this, smart contracts are running much faster. Another thing why it is easy to build is because you have directly audited cryptographic libraries in the virtual machine. Schnorr, BLS, Edwards, signature verification, signature creation, elliptic curve mathematics, big float mathematics, managed maps with iterators directly inside, and even zero copy serialization for internal smart contract structures in the internal application. Soon we will have ZK proofs, like validating your ZK proof directly through an VM endpoint. All this means is that when you want to develop your smart contract, you do not have to think about any of these things. You know that those are offered as an API directly from the VM, that they are audited, they are secured, and then the only thing you need is to call those. If you think about like for other blockchains, most of the times you would need to search for the library which implements such mathematics, and then or cryptographic verification. Then you have to see how to use those, and then to call another smart contract actually to do the job for you. In this guide, you ask the VM to do the job for you, and again, it's much faster as it's actually executed at the bare machine level, and because it's faster, it's cheaper to call. For smart contract developers, the gas will be less and less doing this. One of the new things which will come with RC 1.6 is managed maps. So everything from managed buffers, big floats, big integers, which are kept in the cache and in the buffered cache for the smart contract, will have managed maps as well. So you can just throw your objects inside it and then iterate over your map or search in your map and all kinds of things you want when you want to do complex processing at the smart contract level. Another thing, how do we help smart contract developers to build their things, is enhancing how smart contract to smart contract execution is done. And we see that there are a lot of problems here and there on the blockchain space. We see a lot of attacks, and we thought that, okay, we have to, if we can, why don't we help developers to build new things with new endpoints, which are much safer and much secure. One of these things are, for example, transfer and execute, which directly transfers tokens to users or to other addresses. And it's actually super safe. It's much safer than EVM token-based transfer phone functionality, but we will speak about that a little bit later. So for synchronous calls, you can use execute on destination context. This ensures that your the smart contract which you call have to exist in the current shard. It's executed, you get your result instantly, and then you can do whatever you want with the result. One fun fact or fun thing here is that you do not have to call revert at any time. What you have to do is, in case you want to crash your whole execution, you just call the VM endpoint of return error, and then the VM will clean up everything for you. No tokens are lost, no storage is written, everybody is happy. The transaction consumed only gas, and then it's okay. For library calls, you have the execute on same context. This means that if you want to allow another smart contract to execute on your contract, this is used for libraries in general. We do not necessarily use this in kind of development for our own product. We tend to separate components and do execute on this whenever it is needed. Transfer and execute is a model in which you want to transfer tokens or not transfer, but execute something, but you do not care about the result. This way you can launch a few, let's say, operations, and you know that they will be executed, but you do not care about the result at all. And this works intra and cross-shard as well. As we are a multi-sharded environment, we need a model in which smart contracts can call another smart contract and to have a result back. For this, we developed the asynchronous calls with callbacks, and which enable smart contract developers to build shard agnostic, because the VM and the whole protocol will arrange for you whether the execution have to happen in your current shard or in destination shard, and will ensure that the callback function is always called, and the callback function is called the same way whether it is intra-shard or cross-shard. So the smart contract developers doesn't need to care about it. What he needs to do is, when I call an asynchronous call, I have to define the callback, and on the callback I have to decide what do I do if the asynchronous calls was success, was an error, or was success with a token transfer and with some results, and do something with those results. What we saw, for example, when we were developing the X-Exchange smart contracts, especially with the energy smart contract, and after that with the safe price module as well, is that as a developer, you would like to read storage from another smart contract, do some computation on it, without necessarily calling that smart contract, because that smart contract might not have all the library computational function you need. And why would I need to spin up a smart contract, execute a get function from it to give me some results, when I can just directly read from the smart contract storage from another smart contract? So we implemented this kind of endpoint directly to the VM, in which you can read from other smart contract. Yes, there are some use cases where developers do not want to let their smart contracts to be read by others, because you would offer get functions and developers would pay for it in kind of subscription, like in Chainlink. And then the smart contract developers who deploy their smart contract can set their metadata properties, whether the smart contract is readable from other smart contracts or not. So it's always your choice. The same way, we saw a few problems with Ethereum, for example, with payable or non-payable things, as users tend to lose funds with when they were sending tokens to a smart contract which was not payable. And it is pretty hard to resolve these kind of things on EVM, and not all the protocols, DeFi protocols, support such things. So we ensured from the protocol level that we have a set of properties like payable or payable by smart contract, which means that if a user or an address sends you some tokens and does not call any function from you, then the transfer will yield an error, and the tokens will be returned back for the user. So the user is always safe, and it's easy to integrate, and the user cannot make mistakes easily. That's the thing we want to resolve, is that the user's funds should always be safe, and the mistakes he can do to be limited. And that the same with the developers. We want to offer these kinds of endpoints and this kind of support in order for a developer's experience to be better, and for him to not make mistakes easily and to develop faster. Another thing we saw, we are in technology, and in technology, even if they are smart contracts, we are always building new features. So we built the upgradable property inside, in which you can upgrade your smart contract. However, what we do is that in general, we would put the ownership of the contract to a multi-signature, and the multi-signature smart contract would upgrade the underlying smart contract. This would mean that the smart contract is verified before, or a DAO verifies your smart contract, and it is safe to upgrade, and and users do not have to necessarily concern about it. So simple smart contracts are developed. By the way, simple smart contracts which do not interact directly with other smart contracts are shard agnostic. And most of the smart contracts are like simple. A liquidity pool which wants to do an automated market maker, it's actually shard agnostic. He has an endpoint in which he receives some tokens, he does a set of operations and transfers the tokens outside. So it's simple. He doesn't have to care about which shard he is in. If you want complex smart contract to smart contract calls, it's a decision you want to make, and you have to make and what kind of API to use, depending on whether you build in shard or cross shard. But one thing you have to know is that even in shard and with one shard, we are the fastest when it comes to smart contract execution. To solve composability in a sharded environment, we tend to innovate in the asynchronous models. Right now on the mainnet we run with asynchronous V1, we call it V1, and then we will start to work on asynchronous V2. Actually, we already worked like 2 years on asynchronous V2, and it will be launched next month during the RC 1.6 mainnet launch. And we are already working on V3. This will not take us 2 years because it's much more simpler. Furthermore, I will explain what these kinds of asynchronous calls means. So it is easy to build again on MultiversX, and seamless smart contract to smart contract execution on cross-shard environment is ensured by asynchronous calls. And once you get the idea about the asynchronous calls, it will be pretty easy for you to solve all your kinds of issues. And we had a few feedback. For example, we look to feedback when even for auditors. So auditors would take and make an audit on a new protocol, or for example, a liquid staking protocol, and they would discover that, okay, this kind of edge case, if the developers use these kinds of endpoints, it's in a little bit wrongly manner. Then what we tend to do is, first, we try to fix it on Rust framework directly if we want a fast launch. In this case, for example, it was that after an asynchronous call was launched to issue your ESDT token, you should put like a small time lock there in order to not mistakenly do not issue your token twice. We tend to do that at the smart contract level, at the Rust framework level, and then we enter in deep inside the VM code or the protocol code and implement new features which would enhance interactions and which would make developers to not care about these things and to resolve the audit part by default from the framework or from the VM or from the protocol level to make it easier. So asynchronous calls V1 exist a few years since the mainnet exists. What it does, it allows smart contract developers to execute one asynchronous calls. When the asynchronous calls is called, the execution of that smart contract is stopped completely. The child smart contract is called, and the accumulated result, tokens and result from the child execution is returned to the parent, and the callback function is called. The smart contract developer, parent smart contract developer, can limit what kind of guests to be used for the child code and callback, but that was like all the options. Although, well, if some smart contract developers needed multiple asynchronous calls, there would be a way through a proxy contract and execute on that on the proxy contract, and the proxy contract launches the asynchronous calls for you. But let's say it would be a little bit complicated and would mean that like rather complicated architectures. And we saw that, okay, we can resolve this directly in the VM, in the protocol, and we came with asynchronous calls v2, which will be launched in RC 1.6. In async v2, parent can register as many asynchronous calls as he wants. For each of those, he can define another callback function or the same callback function. Multiple callback functions can be set per multiple asynchronous calls. And then he can set also the minimum guess needed for his own callback. This is important because by doing this, you will always ensure that your callback is called with the minimum guess, and you will know that you can execute your callback in the success. It's still important to write your callback code in such a way that it executes in a success. Even if you encounter some errors, do not throw error in the callback, but write it to the storage.